I'm the lead developer of the ML team, machine learning team. I'm Giulio Alessandrini, and I'm chatting with you from Italy today. And so today, in this episode of this live chat with Wolfram developer, we are going through our latest edition in machine learning. And I also want to give us kind of an overall of our core machine learning functionality and also where we are going from this point onwards. So I will be receiving your questions live. So if you have anything to ask about what I'm talking about or other things, please write your question down. I'll try to answer them at the best of my ability. Okay, let's begin. And so I wanted to start quickly by going through the evolution of the machine learning capabilities in the Wolfram language. So we started early in 2014, mid 2014, just before the deep learning revolution. So we started adding classical machine learning capabilities with the classify predict functions, which we're going to see a bit more in detail today. Then we moved to neural networks with the image identify project, one of the early microsites where you could identify your images, and then this was folded into the language. And then year after year, we added we tried to add all the elements of the standard ML pipeline, dimensionality reduction for vectors, entity tagging for text, automated feature extraction, train capabilities for neural networks. Then we have this also related to dimensionality reduction and feature extraction, visualization in this more visual-oriented way. We added audio support, video support, and I mean, anomaly detection here, distribution modeling. So it's kind of basically core pieces of the ML pipeline that has been coming together. At this point, while we are covering many facets of this, the focus is shifting more towards high-level support, keeping the data scientists in the loop with interpretable machine learning, and external system support. We want to support external frameworks as best as we can, and we're going to go through that during this talk. Okay, so I already told what we were talking about, so we can skip the outline and go straight to the content. We have been demoing functions like classify and predict for a long time, and they have been growing a lot internally while keeping the same interface in respect to the outside world. How do you, as a user, use them? So it's quite simple. You take your data, like for example, this is the famous Titanic survival dataset, where you categorize passengers and try to predict if they survive the crash, the shipwreck or not. And this is quite easy to just plug them into this classify function. Here I'm asking for a higher level performance goal to be quality, so high accuracy in spite of time. And I just want to name my features to reuse them later. And this I can run this live. This is pretty fast. This is doing some magic inside, and it's giving me a classifier. And of course I can run this classifier on this input. And maybe I predicted correctly. Yes, I predicted that correctly compared to this training set information. But there's a lot of magic going on here. So as much as it's nice to be able to have something usable immediately, it's also good to be able to explore what's going on. So let's go through that together a bit. So this is a complete pipeline of what we're trying to do in our automated machine learning high-level capabilities. So you've been providing things like input or targets to the function, which is basically the only thing you have to provide. And then when these things come inside, a whole variety of things happen. The first thing is we need to extract features from your input. So in this example, we provided numbers, which can be tagged with quantities, can be years, can be minutes, in this case is years. Strings like male, female, it can be text, it can be real numbers, it can be Boolean values like true, false. And not every machine learning method is able to deal with this variety of input. So what we want to do is we want to automatically convert them to like a vector of typically a vector of real number or a vector of categorical options like A, B, C, if the method can handle that. Then once we have these features, then we have to pick the right configuration. By configuration, we mean one method like logistic regression or like gradient boosted tree, random forest, and a set of parameters that define this method, like how many trees you have, how deep they can go. Once you have these, then we can basically take one of these and train it on the original data. The magic about mathematical machine learning is that we don't just do one training. We do many trainings and we compare them and we try to pick the best out of them. And it's important to understand what is going on because you can let it go fully automated, or you can run your specific configurations. So let's have a look at how this can be done. So the first part of the pipeline I mentioned was feature extraction. So this is what the classifier that I trained before, and I can basically grab what feature extractor has been selected in the automatic pipeline. And this returns me a feature extraction function that I can then apply to the data. For example, here, class, age, sex. And in this case, the selected method was able to handle with nominal quantities with categorical variables. So I get this thing is compacted in one numerical vector and one categorical vector to encode the class and the sex. So this is the first challenge that we are working on right now. We made it possible to extract this function, but what we would really like to do is to give you even more fine tuning. So of course you can specify the feature extractor when you train, but our internal representation right now, and this is internal code I'm just showing you because it's a chat with the developer, but don't take it for granted. So it's a tad more complicated than what you're exposing right now. So the first challenge here is how do we expose a complicated pipeline, making it simple? So here you can see what you're doing several things. We are synthesizing missing values. We are converting everything to vector. We want to standardize vectors. We might want to do more things like if your data spans different scales, we might want to do a log transform to compact the range. So all these things, you can let them happen automatically. And sometimes that is good, especially because training these things is fast and having one round of the automatic pipeline is going to suggest you a lot of useful things you might not think about. But it's also good to be able to control them manually. So the challenge here is to find the right balance between easy to access, fine-tunable pipeline and a helpful automation that is going to kick in whenever you don't specify a thing. Okay, this for the feature extractor. What happens when we have features? Then we have to try different models. And here you can see that I can use the information function to extract from my train classifier informations about what happened. So you see here, what we have been doing inside is we have been chopping the data set into increasing chunks. So like 10 examples, like this around 50 examples, around 150 examples. And this is close to the full data set. And at every step, we find what the best method is. So for the small data set, it was random forest. Here it was logistic regression. And then here it stayed logistic regression with slightly different parameters. And And you can check in here. So this is the accuracy, but you can check in here, like everything that we tried inside. So basically, in those few seconds that I've been training in the first slide, different methods like naive Bayes, random forest, different type of logistic regression, decision tree, they were tried and tested. And they were tested splitting the original data in many different chunks and trying these models, like training these models on some and testing these on others. And at the end, we can get back exactly the method and all the other parameters. So the parameters that are not defined by the data, but that define the method themselves, that have been found in the automated pipeline. And why this is useful? Because once you have found what you're looking for, then you can skip all this automation and go directly there. So here, for example, I can train a classifier using same data, but I can just use the method option of the previous one, and this is going to be very fast because I don't have to try anything. If I don't want extra information via cross-validation, but the splitting of training and testing, I can even specify that I just want to train directly, no magic, just train, and this is even faster. So I don't know, while I'm streaming this live, what are the timings? So they're slightly slower than what I had before the stream, but you see that I was spending 3.4 seconds in the original training, testing all the possibilities, and going directly here with a little bit of validation. I have 0.3 seconds, 0.35, and then I go below 0.2 seconds if I just don't want to do any validation at all. So this is a key, like being able to decide yourself between this time, exploration, quality, speed trade-offs. These all trade-offs that we're trying to offer here, and we want people to be able to choose from. And why it is important to choose? Because, of course, I could just pick a method myself here if I know. I'm going to lose some stuff though. Like we can use this information function on the original classifier, and this is going to tell me some things like this accuracy, for example, is being estimated during the cross-validation phase. If I ask the same thing on the classifier that I trained without any cross-validation magic, then I don't have this information. I have to compute it myself. So this is the key. Either you let the language compute things for you, or you go for maximum speed, maximum control, and you have to compute things on your own. Okay, so just to summarize a bit, what we are focusing on right now, that you are getting a little bit in version 13.1.2 and a lot more to come in future versions, is a lot more reporting on what these functions are doing, similarly to what you've seen here. Like these things are going to grow, are going to be more detailed, are going to be more interacting, more in a way that you can interact with them, and we're going to propagate all this from functions like classify and predict to functions like clustering, missing imputation, anomaly detection. The biggest challenges, one I already mentioned, is providing a true, fully fledged processing pipeline where you can have very fine-grained control, but also very easy to use, which is a big challenge because, of course, fine-grained control typically means that you have to specify everything yourself, but this is not in the spirit of the machine learning framework that you're building here. And another important things that we know we are missing and that you're working on right now is out-of-core training beyond neural networks, online training, and even more advanced optimization techniques while sampling configuration. The idea here is to make the most out of the time you spend training. Okay, once you have the model though, what do you do with it? I mean, of course you can immediately run predictions, you can run classifications, but typically the model itself can be used to analyze your data in different ways. So one thing that you are currently working on is like high degree of interpretability for what the model is telling you and for how it can be used. The first thing to achieve this is to have a good set of measurement on the model. So here you see I'm taking from the same, oops. Don't understand what's going on. Sorry, I lost my screen. Whoop, I'm back. Okay. Development version, risky. Okay, back in town. Yep. So this I have my test data for the same data set. This is important. These are data that were never seen during the training of my classifier, and I can use functions like classifier measurement to build immediately a whole load of useful information measurements about my classifier. So here you can see some recaps. This is a logistic regression classifier. This has been trained and this has been tested, sorry, on almost 400 example. And then I had things that I couldn't see with training alone. So what is the accuracy? So here this is achieving 78 point, like almost 79% accuracy on my test data. This is very important. You can see the baseline for your accuracy because of course you want to do better than dumb luck. So this basically is what's going on if I'm just always giving you the most common class, the mode of a distribution as a prediction. I want to be better than that at least. And then it's telling you a bit more benchmark properties and very useful thing for classification, which is the confusion matrix. So these things for a long time have been returning an object. And the usefulness of having an object here is that you can then pry into this and extract all the specific properties for your further computation. So you can get the confusion matrix out alone if you need it in a report. But if you want to play with it, you can get it in a matrix format, not in a plot format, to have your own visualization or your own computation of this. Then you can get, of course, classical statistical measurements like the receiver operator characteristic curve. This is going to tell you how the recall increases while allowing more false positive rates. Like a perfect classifier will be very high here. This is a very noisy data set, so it's very difficult to get high precision in the classification. But we can see here how we could, like, for example, for this problem, it's very difficult to get perfect recall unless we basically allow everything to go through. You can get also more subtle properties like the calibration. This is very important because some models can be overconfident or underconfident. So you know what the probability of being something is if you have a test set, like in a frequency sense, and you want to be sure that the predicted probability of your model is actually matching this probability. So some models are typically very underconfident if they give probabilities that are too low, or you can push them and be overconfident and get probabilities that are not matching what is really happening. But these are like standard measurement. You can get many more than like here. we can check into standard stuff like accuracy, accuracy baseline, whatever you have seen in the original panel. You can get things like the residuals, and okay, no, this is not a prediction, so no residuals, but you can check stuff like classical statistical things like F1 score, and you get one for each class. A lot more people died than survived, so we typically a little better predicting dead people. And what I want to show you, yes, here. But you can also get like more advanced things like probability histogram, like the actual plus probability versus what we are predicting. We can check the example that were correctly classified, that were wrongly classified. So you can explore this, and basically you get a lot of standard information about your classifier. This thing is that is pretty standard, but while it tells you something about the performance, and it also tells you something about possible biases, you might notice from here, for example, that a lot less people have survived. So even if the number of wrong guesses, like dead people predicted to be surviving, and surviving people predicted to be dead, is roughly the same, there's a lot more impact in this case, because like the relative error is bigger because we have less survived people overall. So like these things you can immediately start building your own analysis using this, but it's not really helping understanding the why. I mean, what's the connection between the properties that I use in my input set, like the age of the people, the sex, and the class they were traveling in this specific Titanic case, and their survival probability. So, okay, let's see. This is something that we added in recent versions to try to address this. So this whole system is built on sharp values that are kind of they were originated in like game theory, and the basic idea is to allot the right credits when you have a problem which is handled by multiple people. And this is very similar in a sense because we have different features. So let's bring them back. We have different features: the class, the age, and the sex, and then we have a probability for an outcome, survived or dead. And we want to know, and this is important to understand what these models are doing to kind of pry into the black box. We want to know what are the relative weights of these. Yeah, like this model is telling me that like all people are dying or surviving. Like, is this something insightful? Is this because my data is not correct? Is this because there are some biases that I have to remove? So, especially when these models are being used for this decision that can have bigger consequences, you want to be able to have as many insights about them as you can. And the first thing we can do here is to try to plot the distribution of all these little contributions, all these little impacts, we call them, that each feature has on the final result. So this is already telling us something. For example, this is a two-class classifier. So you can see that these two things are completely symmetric. So we can just focus on the survived outcome, and everything will be true in reverse for the died outcome. What we see here is that the impact of sex is bimodal. So this suggests, I mean, this is not a surprise. We have like two possible values, but this suggests an immediate analysis is this like all male or female? Spoiler alert, yes. We see that age has a large distribution, but is mostly centered around something close to 0. So age will have some effect, but mostly has a little effect. And then we have the three model, like tree model. Can you say that? Like three main chunks of contribution from the class feature. And again, this most likely will map into first, second, and third class, but we want to do a more detailed analysis. So what's going on here? This function is basically taking my model and I'm using keys here to take all the unlabeled data. And he's trying to basically masking each one of these in all possible places and try to predict basically the effect of a specific feature being one value or the other on the final result. There's a lot of computation happening under the hood here. The neat thing about this is that this is the property of the model, not really of the data. So the data is just a mean to an end in this case. So we can, like, leveraging the property that our automated pipeline is building an automatic imputation system. And this imputation system is used to impute missing data, which is something which is actually very, very common in real-world data sets. You might have data with when one or more of the features are missing. Actually, I can show you. I can use a synthesize missing value function, and I can use this distribution. Let's give it a name. This is a learned distribution. This is the distribution of the data learned from the data. And then I can, for example, take something like this and say, well, of course, this is not going to give me anything, but let's say that I don't have this. So this would be a bit of a 50-50 probably, because I mean the passengers are like roughly the same, but I might be missing more properties. So this is going to impute, in technical terms, these values based on the overall distribution of the data that has been looked at during the training. So it's basically exactly using an estimated distribution of this instead of this. And the thing is that you can then extract a lot more of them. You can use this also when you don't have the data at hand. So here I'm simulating 500 elements and basically checking what happens with the simulated data. And you see that I have, just to confirm, to reiterate that it wasn't something tied to the data, it's something tied to the model. I see a similar behavior, like bimodal on sex, and this similar impact on, I have slightly less points here, so it's less fine grain here, but mostly impact of the age centered around 0. And I'm going to explain in a moment exactly what this 0 mean. So yes, basically, well, let's see, I can probably do a little more and see like 1,000 is closer to what we had there, and see if we get a very similar plot to this. But in most cases you should, unless your data has very weird distribution and we were not able to model that correctly. But of course, always in the spirit of being able to fine-tune things, you can also pass a distribution to the classifier before the training. And this way you have, again, full control. Okay, but this is just a distribution of impacts. What we want now is that kind of dig deeper. And here I already pre-computed the impacts plotted against the value of the feature. So here in the previous distribution, we just see what the distribution of impact is. Here we can look deeper, and we need to split for each feature and check what's going on. So you can see, again, this is symmetric. So we can just check, for example, the survive case. We can see that going from first class to third class is bringing down the probability of surviving, which is what we expected, but it is nice to check. And you see that these things are compact, like I don't have numbers like points here or here. So like all first class passengers, like compactly, I mean, this is what the model thinks. Again, this is the property of the model. So it's very useful to check it like for biases. Like this model like is constantly assigning better probability of people in first class, which for an historical accident has the importance that it has, but if you know if you're gonna to use this model to predict the current outcome, you might really want to double check what are the assumptions made by the model. See that second class, as predicted, not very much impact, probably as many people died as survived here. And third class was really, as we know from history, people in third class mostly didn't make it. And also something that's to be expected, but the model decided to basically model the relationship between age and survival probability as mostly linear. Has probably some noise to the integer values in the training data, but yeah, this is mostly linear relationship. Like the older you are, the less likely you are to survive. And also female, apparently, the model thinks that they have much higher probability of surviving than men. And again, this is something confirmed by historical data, but it's useful to be able to see that the model is picking this up. And again, this goes more into details, but it's still an aggregated view. So we can go even more into detail by checking for each single example, what are the changes that each feature value had on the final result. So now it's time that we look at a little bit at what these numbers are, because like typically I've been talking with probabilities a lot here, but if we look at these values, they go negative, they go above 1. So what's going on exactly? These are not probabilities, these are log odds. And what are log odds and why use them? Okay, let's do things in the right order. First, in my training set, I have some prior, means like I have some assumption based on the data about the outcome. And we saw this when we had the baseline accuracy, that just predicting the commonest class was giving me something better than 50%, for example, for this binary problem. And this is because like 61% of people died here in my training data, and only 38% survived. So these are like prior probability based on the data. And the reason why these are not in the 0-1 range in the plots is because we are not using probabilities, but we're using log odds. So log odds, like odds, you might know them if you bet, for example, like I have like 3 to 1 chance of or 1 to 3 chances of this horse winning the race, typical example. And log odds basically very easy to get from probabilities, because it's the probability divided by the complement of that probability. So in this case, it's basically probability of surviving over probability of dying. And then we take the log. So why we do this? Well, this is what our model is predicting. And the probability is between 0 and 1. Predicting something between 0 and 1 is very difficult, because you have to not just predict a number, but also learn the constraint. Learn that it has to go to be above 0 and has to be below 1. If you take the odds go from 0 to infinity by construction. And the log of the odds has 2 desirable properties, that it goes from minus infinity to infinity, making this an unconstrained problem. So I don't have to learn any constraint. And also it allows me to span easily, like a much larger scale. Like I want to be able to predict very low probability, very close to 0, very high probability, very close to 1. And this is helping me doing that. Okay, so now let's check. If we take only one of these, for example, this point, this is one specific set of class, age, and sex. And here I'm looking only at age, but I want to be able to track down what's going on. Here, for example, I created 3 examples. Just sex male, or the rest is randomly imputed, just age 30, or just class first. And we can see here what's going on. Again, these 2 are symmetric, so I'm going to drop die from this point on. But you can see here that when I say sex male, which is, 1 second, I should have nice tooltips, but I'm not seeing full screen. Silly me, sorry. I'll just go back from full screen. so we can see the tooltips again. Maybe it was a presentation mode. Let me check here. Silly me, I don't see the. Okay. Oh, I need to get only one class to see this. Sorry. So all classes, and then I just want to be survive. Survive. Here we are. Okay, let's go big again. Okay, so here you can see what's going on. So this blue line is where everything was imputed except for sex. And you can see that the first effect of class here was pretty small. So the odds are like starting here. These are the default odds of surviving, which is the prior odds of surviving, which is this minus 0.47. And yeah, the randomized class didn't affect this much. Sex being male, which is what I forced, is bringing the odds down. And the random age is, in this case, bringing this slightly down, but I can simulate many of them to basically exclude the effect of class and age, just check sex. In this other case, I'm just using age. See, age of 30 is pretty neutral. And in this case, I'm forcing class being first class. And you can see this has a massive impact on survivability. I can also check, for example, I can study the impact of class being first, second, and third. And here I'm just selecting the class property for this. And you can see here, class third, class second, class first. This is splitting the probability, or like the odds, and then the probability of surviving. And of course, now like you understand a little better, like what's going on here. You start from the prior, then you add features one at a time, and you end up on the final result. So this is what the model will be predicting. We can check these. Actually, not just age, let's check all of them. We can check with all the distribution of, for example, training data or test data. And we see here that we have this, what we predicted, we have this big split based on sex. And if you hover this, unfortunately, the tooltip is a little small, but if you hover this, the sex is always male here, and here is always female. So you can confirm indeed what we supposed initially, that this model is splitting along gender here for estimating the probability of survival. And then here we have another split due to class. So all these people are third class. These people that are going in this other direction, they are second class. So being male and being in second class makes your probability of survival like a little better. Being male and first class, according to the model, makes your probability of survival a lot better. And we see a similar split for like being female. The model thinks that if you're first class and female, like you probably make the most out of it. So these two properties alone are basically telling almost everything you need to know if you're female first class. And then as we noticed in the regional distribution plot, the impact of age is very limited. You see, these lines are mostly straight. There are some lines like this one here. So this is 57, for example. This combination, the age had big impact. Or like this thing here, age 2, like infants were saved more than most. And here, like 66, elderly people had a worse chance of it. So basically, like looking at this, you can really drill down into the model and try to figure out what are its biases, what are the reasoning that the model is doing. And this works with all the models, basically. You will see different structure here, depending on the model that you pick. Like the decision tree will tend to exhibit more. You will select the different groups based on the splits. like continuous model, you probably see less, like as you can see here with age. Like we have continuous model and continuous variable, so the prediction is more nuanced. And these things are very useful to understand that the hidden working of what is otherwise a black box. Okay, so just before we move to the final bit of this, which is more focused on deep learning, of course, we are not done on interpretability. The goal here is to make even more things explainable. We have a nice project that hopefully will see the light soon, like in the next version or so, to explain what happens on models trained on images, like what areas of the images were used to predict a class or a position of the object or things like that, that can be used to test your models and see their assumptions. And there's counterfactual explanation, there's causal reasoning, there's a lot of things that would be nice to add here. And I hope that sooner or later you will just see all of them. But this is just a start. Okay, another area we are focusing a lot, of course, is neural networks or deep learning. Just a super fast recap. What are neural networks? They are like small programs, small formulas that can be combined and are differentiable. This is a core thing here. Like another term for neural network is differentiable programming, because you write programs with derivatives, and derivatives tells you how these things change, and knowing how they change means that you can use optimization on them. So here you see this, I think, is an object detection network. You see this has like we tend to group things in our framework. This takes an image, has some initial analysis, processes at different scales, and then creates values for probability of object, probability of class, and where the things are. But of course, this is not the real stack. The real stack is this one. This is a really large set of differentiable operations. And it's stacked all the way to the end. So the complexity of these things is it can go very high, very fast. And you are doing a trade-off here between this excess complexity and the power and flexibility it allows you. So here, just a quick, like, given that we did this Titanic problem, like I like to show you how you solve it within the neural network system. Here you have to do everything yourself. Yeah, so you define operations like linear fit, like the normalization of the output, and like a normalization of probabilities. So here I define these as functions, and I can either build my computational graph, or I can use some more like programmatic approach and write these things like a function, where it takes like some input. I apply a linear fit with 10 outputs. I normalize it. I use nonlinear activation function, and then I do it again. But this time to the output of my linear operation, I sum the input. This way, I'm basically creating what is called a residual unit. It's very easy to write this way. And so I'm fitting the residual of this operation, the difference, compared to the original input. I'm doing the same thing. And then, I opened the documentation by mistake here. And then at the end, I want still to predict probabilities. So I need 2 units of linear fitting and a final softmax to normalize these to probabilities. So we have still some goodies that you can use to make this easier. So I have this still original problem, and let's remind us what it was, of data in different shapes. Of course, this thing wants numbers. So I'm just say, okay, use a feature extractor here. I can pass a feature extractor on the classifier, for example, or I can just leave this unspecified, and this will be trained together with the weights, with the parameters of these linear models. And instead of the 2 numbers, I just can say, okay, just interpret these 2 numbers as class probabilities for survived and died. So this way is another little piece of goodie. I can use data in this form. I don't have to provide the vector probability here. So this is quite concise code if you know what you're doing to define a network, and then you can train one. And yeah, this is not going to be that long because I'm just posing using some validation set here. I can do some tests, and you see this basically the neural network version of n-minimize. And yeah, this is like in a nutshell what this framework can do. And you can then train this. This gives you an object here that tells you what happened, but you can always extract a final network and apply it to the input. Let's try to apply it on the same input. Yeah, and you get the output out. So this is the neat thing. You can use these things as functions, and you can just inject them in your pipeline. This is what the framework is doing. So this accuracy here is like comparable with like a little less what we did with full automatic thing. Even if the fully automatic thing was kind of a bit less powerful than the network I put on together here. But yeah, this is basically what you've been able to do for a while. What we're focusing on here, and we added something for this latest version, but I want to tell you a bit more about what we want to do here, is first to expand this and make this completely independent of the backend that you want to use. You want to use PyTorch, want to use TensorFlow, JAX maybe in future. Like, want to be able to support all these backends completely, like detached from the syntax you use here. So you still have a very, very simple way to write things, and you can just target to whatever you want. The first step in this is that we've been adding a way to bring in models from the outside world, training these different variety of frameworks, and run them directly. So as we have seen before, like training a complex model can be jarring. You need data, you need to know what you're doing. It's much easier to get a model from outside and use it in your pipeline. Okay, so the first step that you're doing here is we target the ONNX format, which is an interchange format. You can convert to ONNX from PyTorch, from TensorFlow. From ONNX, you can convert back to, for example, what's called CoreML Metal, the one that you use on Apple devices, Qualcomm specific formats for example, driving applications, and the thing is, you can do now in this. I'm using a 13.2 early build. Is you can just get a model from the outside world, and you can load it as an external model. So this thing right now you cannot train it, but you can use it right away. Then this has been optimized to have minimal overhead. This is basically just running the ONNX models. And of course, the next step here would be to add support for PyTorch models and TensorFlow models that can be run right away. Longer term, what I said before is to support different trainings. But shorter terms is just to allow you to use any model that you want. And you can see there's just very, very minimal overhead compared to the just few metadata. This is a very nice compactified, quantized model for face detection, and is 1.5 megabytes. And you can see like very little overhead compared to that. So this is very close to Metal. This doesn't have all the abstraction that we have in the high-level framework. It doesn't have automatic batch detection. It doesn't have encoding and decoding of special input like images. But we want to give you something as soon as possible that was very fast. So it's not too difficult to add this yourself. So I'm just gonna add a little bit of code to convert from image to tensor and to add batch dimension. And then bam, I can run this and get these things out, like scores, boxes, position for the face positions. I can, again, with a little bit of code, recast this into a format which is usable in our vector graphic system. And then bam, I can plot it. The only difference here that I did is to add this function from our Wolfram function repository, which is doing no-max suppression for boxes. Basically, I mean, you can see what it's doing here if I lower the threshold a bit. This is probably, maybe it's just giving you very, very high very high probability things. Okay, you can see there are more boxes appearing here. If I bring this down, and oh yeah, I did it too much. There's gonna be a lot of boxes now. So what we took, we can wait for this to run. So yes, this is predicting a lot of things, and you want to filter it. But yeah, as you can see, like there's a lot of things that you can do when you have a model available right away, and you can use the rest of the language to deal with that. And it's not just the size; the speed of this thing is pretty good as well. Like this was a small, fast model. Oh, okay, you see, I brought in too many boxes. Let's go back to something more sensible. Actually, let's. Yeah, I think I can leave it. Point. I think 90% certainty seems pretty good. You can see that this runs like more than 43 images per second. So this is not. This is real time. I would say this is real time, but even on a laptop while streaming live. Okay, so what are the things that are happening here? So this thing is going to be in the next release. In the subsequent releases, we are going to add support for runtime support for more frameworks. And the big challenges are expand training and inference support for our native framework, which is a lot more flexible because it allows you to construct networks, modify them, fine-tune them, retrain them. So it's something absolutely that you want to have. And we are working very hard. This is very difficult to simplify pipelines for complex problems like reinforcement learning. And a third thing that is a nice challenge and we absolutely want to tackle is support deployment on a much larger variety of devices. So I added here to this note that will be shared after the live stream a set of resources if you're interested in digging deeper and find out what's going on. Well, thank you. This will just be the end of my presentation. Let's see, I have one question from the stream. What is the complexity for common problems and optimization? Well, it really depends on the model that you pick here. Like some configuration internally are very few parameters. Some other are more complex. We try to balance this by, like, for something like logistic regression, we try to keep the model simple by balancing with something like L2 regularization. I'm not sure that I'm getting exactly the vibe of this question, but I would say that it really depends. If you're asking about the complexity of the automation, that's typically quite high in general because we try a lot of things. Let's see. I'm getting some new input here. Okay, now this is the different questions. Many AI systems develop biases in the sequence of training sets. Does Wolfram system offer a multi-run randomizer for the training data? Well, it depends on what you use. So automated pipeline like Classify, Predict, they are dealing with this internally by reshuffling the data in very many possible ways. This is something close to k-fold sampling, where you take your let's write something here, where you take your training data. Say I have 6 examples, and I'm going to train on this and test on this, and then train on this and test on this, and I'm doing many possible reshuffling. So this is typically a good way to handle this. For something like NetTrain, we are randomizing the data in different epochs. So this is just standard way of doing it. But you can write your own generator function to basically have a customized sampler, and then you have full control of the batches that are sent to the training, like the mini batches. that compose the epoch of training. Probabilistic programming. Probabilistic programming is a tough nut to crack, and we didn't have much time to work on that this year. But I have two developers that are very, very committed to that, and they really want to work on that. So I think I can hold them only for so long, and I think that will be coming. We want to integrate. One reason why we're waiting is that we want to work together with the compiler team to have very effective, so I would say very, very fast, honestly, and differentiable programs for our sampler. So this is one thing that you are waiting for. We are doing other projects with the compiler in the neural network framework to. We have a layer which is completely customizable, which is using the compiler and is using automatic differentiation, and they are using this basically as a test run for more projects with the compiler. Okay, there's one other question about good primer how to encode model data on efficient data model. Genetic programming. I was very interested in that many years ago, and then I lost interest a bit in that, and I've seen also people losing a bit interest in that. So I'm not really up to date state of the art genetic programming. Let's see, there's some follow up. Encode a model problem to beat my style representation. Well, I want to think about it for a second before saying stupid things. So, okay, first answer to this question is like, no, we don't have a built-in way to encode hyperparameters into or like model choice. And you of course you can use categorical variables to represent many things. You could say that. Especially if you limit yourself to a specific class, you can say that that you have like the choice between different methods could be one categorical variable, and method like some continuous parameters could be another real variable. One simple for if you want to use it for neural networks, like you use neural networks to solve this problem. In terms of optimization, you can always embed things, embed the categorical choices in with using one hot encoding and then re-encoding them, or you can use something which is called embedding layer. Sorry, not embedded service. Embedding layer. This is a little bit better than one hot encoding, I think, because it's learnable and it doesn't suffer the same hard cuts that one hot encoded has. So this can be used to encode nominal choices. I can think a bit more about that and reach out with maybe on the community with a more considerate answer. I think I'll have to wrap it up now. So, well, first, thank you for joining me during the streaming today. And I hope you can continue the conversation in other places. And please, come back for the rest of the series. We have many more episodes coming up, and you can find more information in our community. Thank you.